Hello and welcome to the session. I am Akshay Kumar and I will be discussing with you today memory organization and input-output organization. The reference material for this particular session is going to be Block 2 of your MCS-12 course. Now this is going to be a very interesting session because memory is a very important component of any computer system. Whenever we go and buy a computer, the first thing told to us is this is the CPU, and then the next thing is told to that this computer has this many GBs of RAM, and then a number of things are told to us, that is that this computer have cache, this computer also have the hard disk of 1 TB, 1 terabyte and so on and so forth. So what are all these things? What is their significance? How we can relate these things to computer and the speed of the computer? So that is what we are going to discuss in today's session. So what we will be starting with, I'll be discussing with you about the memory hierarchy. Excuse me, can I have mouse please? We will be discussing about memory hierarchy, logic diagram, and then we will be moving to logic diagram and memory chips, like how they look like. Then we go to cache memory, right? And then we will first talk about I/O devices a little bit and a bit of I/O techniques. So these are the basic things which we will be covering today. In today's session, initially we will be discussing, whatever we will be discussing is in general applicable for anybody, right? And as we move deeper into logic diagrams or so, then you have to follow the MCS-12 booklet and blocks, right? So please be very attentive. This is a very important topic and we will be going very deep into this particular topic. So first of all, let us define the memory hierarchy. Now what happens in general, this is what you are going to find, that big memory is cheap but slow. What is a big memory? That is what the question here is. Then fast memories are expensive, therefore small. Okay, and then what are these fast memories? As we increase performance by having hierarchy. So what is this hierarchy all about? So if we can categorize different kinds of memory within a computer system, then the foremost or the fastest of the memories which we can identify are the CPU registers, which stays within the CPU, and the communication to these registers are very fast and they process information at the fastest possible way. And in fact, they are as good as the speed of the CPU. So basically that is what we are saying. This is fast memory. However, what are they? They are going to be expensive, right? So if they are expensive, so they are going to be small memories. Then if CPU is one particular registers, they are the fastest, where I think the flip-flop last time what we discussed in the last session was all about flip-flop based registers are the technology which we use. Okay. Then is the internal or main memory. Alright. Now these memories are also very fast, but may not be as fast as CPU. So obviously they will be of bigger size. And as we discussed in the first session, that is von Neumann architecture, main memory is one of a very important component of a computer because all the instructions and data are to be loaded into the main memory before processing can be performed, right? So this is going to be a very big memory because I want to perform bigger tasks here. So normally today's computer is having 1 GB, 2 GB, 4 GB, 6 GB, that kind of a main memory is available. Okay, but is it sufficient, or my data is still even larger than that? If my data is larger than that, then I'll be needing some of the input-output devices where the memory, where the data will be residing permanently. So probably this memory suffer from another problem, and that problem is that this memory is probably not permanent. Main memory is not permanent because most of that is not magnetic. It is more of a electronics-based circuitry. Therefore, most of these internal memories are not permanent. Therefore, we need the secondary memory which we utilize with the help of I/O interfaces. So this is in general the memory hierarchy. So what is the magnitude? CPU registers may be hundreds maximum. These days hundreds of registers are there within the CPU, but not more than that. Okay, then internal memory, as I talked about, main memory is going to be roughly 4-5 GB, but cache memory is going to be smaller. It is in the size of few MBs only. So we will talk about cache sizes a little bit later. And then input-output devices. Many of these devices you will be familiar with. One of the most common is hard disk, and the second is the optical disks. So we'll talk about those. And what are these I/O interfaces and why they are needed? This is what also we'll be discussing as we go along. So this is in nutshell memory hierarchy is. And what is the memory hierarchy? Memory hierarchy is that small memories, faster memories are lesser in size, and bigger memories which are cheaper, having low cost are very big as far as size is concerned. So first, then we start with the DRAM, not DRAM, SRAM, static RAM. Now, what is static RAM? Static RAM is a flip-flop based memory which basically is utilized in registers and many of the cache memories. Now, how they look like and what is the cell of a DRAM, SRAM, wherever I am saying this is SRAM, static RAM. This is a flip-flop based. Now look into the flip-flop. It's a very, very interesting kind of a flip-flop what you see. It's a JK flip-flop, and in JK flip-flop the characteristic table is shown over here. So now what can be the two states? Now this is basically only a cell of memory. Whether this particular cell has been selected or not, that is going to be determined by select input. If select is 1, this particular cell is selected. Now it is a random access memory. So what are the two operations on the random access memory? Either I can read from it or I can write on it, right? So these are the two operations. Now if I want to perform read operation, now what is the memory per se? The memory per se is just what is the content stored in this particular flip-flop. Now what can be those values? That can be, if the flip-flop is in state set, that means memory is having value 1. And if the flip-flop is in state 0, then the memory is having value reset or 0, right? So this is what is the basic value which will be stored into this particular memory location. And when the select signal is activated, we will either read or write. Okay. So first we start with the read. Okay. Now what happens if read is basically what you see here is R and W dash. That means if this input is 1, the process out of this particular memory cell will be reading process. And if the input is 0, then you will be writing into this particular JK flip-flop. Now how do we do that? So first start with the read, which is simpler. So if I say read goes to 1, look into the AND gate here. Okay, so C AND gate will be activated. Alright. So JK flip-flop, suppose it contained a value 1, what is going, and the select input has to be 1. Otherwise, there is no point talking about this particular cell. When this particular cell is selected, only then this particular output will be obtained. So what happens? Select is 1, read signal is 1, and whatever is the value of Q. Suppose Q is 1, the output will be 1. If Q is 0, output will be 0. This is an AND gate. AND gate is that all inputs, if they are 1, then the output of AND gate has to be 1. So this is the way you will be getting the output. Whatever is the value in this stored in this particular JK flip-flop, that will be output. So technically what has happened? You have read the value of the flip-flop, whether it was 1 or it is 0. Any of the value, it has been just read. Alright. Now the second operation is write. So as soon as, suppose now writing operation. Now writing operation is basically twofold. I'll be writing into this particular JK flip-flop. Either I'll be converting, I want this flip-flop to go to state 1, or I want this flip-flop to go to state 0, and which will determine that particular value? It is going to be the input bit. So if the input bit is 1, we will convert the flip-flop into 1. That means 1 will be stored into the memory. If this input bit is 0, then if input bit is 0, then 0 should get stored into the memory. That is what we want. Alright. And as soon as this write operation is enabled, and how the write operation will be enabled, this write input will be supplied as 0 at the time you want to write into this particular memory, and obviously the select bit has to be 1 even at that particular time. Okay. So as soon as W dash becomes 0, that means what we are feeding here? 1, because this is an inversion gate, right? So W dash 0 will, otherwise it is going to, suppose when R was 1, if this input bit was 1, that was read, this output is going to be 0. So this circuit will not be effective at all, right? Now when W dash becomes 0, that means the output of this gate is going to be 1, and this particular output, this is 0. So this gate is not enabled in that particular sense, right? Something, it will be simply blank and nothing is going to happen in that. Okay. Now what happens here? Inversion. So now we are getting 1 in this, 1 in this particular AND gate. Select is 1, right. So now if the input bit is 1, what is going to happen? The input B, the output of gate B is, which is J, will be converted into 1, and that is what? So output of J, right, output that is happen to output of gate B, which happens to be the value of J, what it will become? It will become 1. That means the next state will automatically go from 0 to 1. So the next state of this particular flip-flop will be, it will go to a set state. What does it mean? The input value 1 now has been stored into the JK flip-flop. Consider this input, and no other circuitry is important in this particular case. Think in terms of that some input bit is 0. In that particular case, this output will be, J output will be 0. When J output is 0, right, when J output is 0, what happens, right? When J output is 0, next state is going to be 0. Alright, K does not matter. The next state is going to be 0 in any case, right? So this particular flip-flop will be cleared. So technically speaking, what have we done? This DRAM during the write operation, depending on the input bit, right, will set or clear the flip-flop. Set means it will put the value 1 into the flip-flop only when the input bit is 1, and when input bit is 0, it will clear this particular flip-flop. So technically speaking, what has happened? You have written into this particular JK flip-flop the value of input, but that change is going to happen only in the next state. Remember that. It's not going to happen immediately. This is the characteristics of flip-flop. So the next clock pulse, this is what you will experience. So this is the organization of RAM. But how the DRAM, but how a cell then can be converted into a chip? So let's look into the chip kind of a situation. So now this 32 into 4. So what we have, there are 32 such rows, right, and 4 such columns of these RAM cells. So 32 rows and 4 columns. That is what we have. Alright. So that is what we have, 32 into 4. So this is the chip, the memory chip. Alright. It can be very, very big also. This is just an example of a very small chip just to explain you how it functions. Right. Then we have an input buffer, and then we have an output buffer. Alright. So input and output will be considered accordingly. Then we have a decoder. Now decoder is a circuit. If you have read your block 1, unit 4, then decoder is a circuit which takes, let's say if it takes n number of inputs, suppose in this particular case it is 5 inputs, n equals to 5, then 2 to the power n, one of these 2 to the power n lines will be selected. Alright, that is how decoder will be. For example, A0 to A5, so this is the highest. So if I say this is 0, 0, 0, 0, 0, then which line will be selected? 0. If it is 0, 0, 0, 0, 1, then the first line will be selected. Okay, only one line will be selected, not more than one. Okay, so this is how a decoder functions. Out of the given 32 lines, based on the input value, one line will be selected. What A represents here? Addresses, right? So these are the memory addresses, right? So these memory addresses are going to select only one of these lines, which memory you are wanting to read, okay, or write, right? So this is how the memory which you want to select will be selected. And this is the concept of random access. You can randomly access any of these memory locations in equal amount of time by just selecting the proper address of that location. Just like your apartments. Suppose there are 10 apartments in your houses, they are numbered 1 to 10, right? So suppose I say apartment number 5, you know precisely which apartment it is. And this is what addresses basically determines which particular memory location you are referring to. So one particular line is going to be here, right? Four RAM cells will be here, and that particular line is going to be selected. Alright, so this is the role of the decoder, selecting one of the 32, right? This is 5:32 and this is 32 into 4. So based on these 32 and this 32 must match, right? Because there are 32 lines numbered 0 to 31, and decoder determines which one is needed. Now this is a typically 2D organization, but let's not worry about the 2D organization. Let's worry about the basic organization here, 32 with 32. Now this 4 represents the number of input or number of output, as the case was in a single cell. One input and one output only. Okay, now this is a read write, alright. So suppose in this is for reading. So you will enable this particular AND gate. Let's not go into the intricacies of it. You can study this of your own, but this will be this input buffer will be enabled only, or will be the output of this particular AND gate, and O here in this particular case indicates negation. No separate AND gate nor inversion gate, sorry, has been made in this particular case. It simply shows an inversion. So what you see, the output of this NAND gate is going to either enable this particular input buffer, that means it will enable the read operation, memory read operation, or if this is enabled, then in that particular case that is output operation will be enabled. So these are some of the circuitry requirements, how exactly they will be working, but you can verify these, that output of this gate will be 1 for read, and output of this gate will be 1 when you want to write into the memory, and output of this particular gate will be 1 when you want to read from this particular memory. So you are reading. Output is resulted when you read the memory location, and selection is which address. This is what is going to cause the selection, that is 0, 1, which memory location is going to be selected. So this is going to select it. Suppose you have issued a read operation of memory. So in that read operation of second location, so this second will be enabled, then this particular AND gate will be enabled, and all the 4 bits will be read into the output buffer. This is how it works, and there is going to be internal circuitry that all those gates will be connected. So that is where which are missing in any case. This is why you have to understand it, you have to extrapolate it. The basic assumption is very, very simple, how the addresses are applied onto a particular line, and then this is for writing and this is for reading. Okay, so reading, if reading is enabled, then the output will be taken from these gates. Whatever line has been enabled, only those cells output will be coming out of this particular situation. Alright. Moving on to the next kind of a situation. What we are having here is a DRAM chip. Now SRAM chip and DRAM chip are slightly different. Now most of you must have heard about the main memory, right? SRAM happens to be the cache memory and DRAM happens to be the main memory. Once again, memory hierarchy plays very important role in this particular case. Why? Because you want a very big DRAM. A small cache will do, but you require very big DRAM. And the DRAM, that is the main memory of your computer, normally range from 1 GB to 6 or 10 or 12, whatever kind of GB you have. Whereas SRAM, whatever we have studied earlier, it may be just few megabytes, maybe 10, 20, 30, not more than that. Okay, because it is more expensive. Now, the problem with DRAM chip is that it basically deals, it's the electronics in it is slightly cheaper. Okay, now the cheaper electronics results into one particular problem with the DRAM chip, and most of you must have read this, that after a while DRAM chip is to be refreshed. Alright, refreshed means the DRAM chip basically it's a capacitor type of memory, so it start losing its content. So it needs to be refreshed over a period of time. So the refreshing itself is going to take time, so obviously this particular chip is going to be slower than the SRAM. Alright, now let's look into some of the things which we can do with this particular DRAM. Okay, so now this is a typically square memory array. Alright. Okay, and this is read addressing strobe, then this is row addressing strobe, column addressing strobe, write and output. Okay, so if you want to write to it, if you want to read from it, that reading and writing remains the same. So we are not going to discuss about the reading and writing part of it. But the important thing here is to understand that this is a different kind of memory now. This seems to be a three-dimensional memory. Earlier what we had is a two-dimensional memory. What was the size? 32 into 4. However, here we see 2048 into 2048 into 4. So basically 4 cells are there and the square memory, the square addresses are there. Okay, now that's very interesting. So there are going to be rows and there are going to be columns, 2048 rows, 2048 columns, and then those 4 cells within each of those 2048 and 2048. So it is a basically two-dimensional array and each array has 4 memory cells. Alright, so two-dimensional array having 4 memory cells. So obviously I need one index just like in an array to support my row and another index just like in my arrays I and j to support the array. Now how these two values will be coming? First of all, if 2048 is the size of each of these, so what is going to be the size of address? Let's say just for 2048, 11 bits. 2 to the power 10 is 1024, 2048 is 11 bits and similarly 11 bits, right? So technically speaking we will require 22 bits, okay, to address this particular memory location. But the number of pins in a memory are very, very important. If number of pins are very, very important, therefore what we do, we reuse certain pins which happens to be A0 to A10. How many bits of address? 11 bits only, right? And this what we require, 11 for this, 11 for this. So what we can use, we can reuse it first for, let's say, selecting the row number and then selecting the column number. And this is what this particular bit determines. Okay, so whatever address which has been applied or which is available on this A0 to A10, if row address selection line, that is row address selection prime, is selected, that means RAS equals to 0, in that particular case, row addresses will be taken and through multiplexer, it will go to this particular decoder. Alright? So basically what we are saying, please note this is very important, that these 11 bits will select one of the 2048 rows, alright, right? And then when CAS goes to high, this goes to this particular buffer. Buffer means we are storing it, and when we enable read or write, the actual operation will occur at that point of time. So first step, enable the row address, so the row address gets stored into buffer. Then enable this particular address, that is the column address. So now the address will go to this particular buffer. So the row address is stored here, column address is stored here. Then you say whatever you want to read or you want to apply. Okay, so that read or write through multiplexer. So row address will select the row. Suppose you want the second row, and if you want the, let's say, 25th column, that is going to be through 25th column. So 2 cross 25th will be selected and 4 bits will be output through this particular sense amplifier and the gate. If you are wanting the read operation, so sense amplifier will read it and they will go to the output. Otherwise, they will be written on. So both the direction, you can see both the direction. Otherwise, they will be written on if the writing work is required onto the memory. So they will be written onto this particular memory. So this sense amplifier will be sensing those 4 bits only. Alright, nothing more than that. Alright, now the question is what this refresh counter is doing over here. Well, if you know refreshing a little bit, why we require refreshing? As I told you, refreshing we require because the content of memory over a period of time loses its content, right? It drops down, and after a while the data will be corrupt and you won't be able to use it. So refreshing is required. But what way refreshing is done? A complete row is refreshed in one go, right? So a particular row will be selected and the complete row, that means 2048 into 4, all those rows will be refreshed at the same time. So this multiplexer ensures that if the refresh counter has been activated, so a particular complete row is refreshed at that point of time. So this is how this whole DRAM chip is going to work. So let's put it in a very simplified word. So what is being done? Either this particular circuitry will be required to refresh a complete row out of 2048 rows. One complete row consisting of all the columns in that particular case will be refreshed, all the columns into 4. Everything will be refreshed in one go, or it will be used to select the row from which has been the address of the next location. So effectively, refresh counter, at least we have to do at least after, let's say, a certain amount of time, let's say few microseconds or less than that, maybe nanosecond, we need to refresh this particular memory, and that is why this memory will require added operations, and that is why this memory is slower, surely slower than the main memory, the flip-flop based memories in that particular sense. So this is the DRAM chip. That is where we have the row address, and that is where we have the column address. We reuse the address lines. Alright, we reuse the address line once for row address, once for column address, then we apply those, that's why we are using a buffer to store them, and then we perform the read or write operation based on the address of which has been decoded through the decoder. So this is how the whole DRAM chip is working. So you can refer to the block now, and it's one of the most interesting circuitry which has been designed in that particular sense. Okay, and this will enhance your learning about the memory, and you will be you can actually go on to learn more about different kinds of memory, error correcting memory and other kinds of things which are there in the market. So that is how your learning curve should be, that you understand the basics and then go on to learn about how the various things are there in the market. Market uses the same concept, but then they put these kinds of things very commercially. Right? So you have to little bit extrapolate, you have to learn a little bit extra, and that is how the whole learning curve starts. But remember one thing, everything is based on simple circuitry, and those are the gates and the flip-flops. Nothing more than that. Gates, flip-flop, and then lots of logic which you have. Okay, every human being have lots of logic. So we can always learn about it, provided we give some time to it. I mean, don't just rush to the conclusion that in one lecture or in one learning you will be able to learn everything. And that is why in my first lecture I said very clearly, the more I know in computer science, the less I start to know about it. because there are huge developments, there are massive developments in that particular area. The less I know, I'm very happy. Okay, no problem. But the more I know, I need to know more and more and more the way the developments are. I need to keep pace. I have to be a continuous learner. And that is what IGNOU teaches you very beautifully. We make you learner who can learn forever. And that is your strength. This is the strength of every IGNOU learner. Given a problem, you struggle, you try to solve it, and you come up with the solution ultimately. It takes time, but over a period of time, you inculcate the habit of taking on the problems head on. And that is the spirit always. I mean, the successful spirit in life is that only, taking all sorts of problems, not just computer science, every kind of problem in your life head on and coming out of it, determining that I will win over it, and you ultimately win. So this is, this has nothing to do with cache, but definitely this is what is our philosophy, that we learn every day some new things and try to learn more. So let's move on to the next step. So we have talked about the DRAM chip, the SRAM chip, right? Now let's move on to the cache memory. Cache is primarily SRAM, okay, but cache now has become one of the de facto, kind of memory which is there in all the processors. So you might find there will be, you will be knowing that each processor is having L1 cache, L2 cache, L3 cache, all these things. So let's know the logic of it. I'm not going to talk about L1, L2, L3 in particular, but let's know the logic, how cache memory also is organized, how the memory content can be transferred and how it can be read. Like ultimately what happens, every access which a CPU wants is from the main memory, right? So that is what is the first statement, that every access to computer is 20, okay, every main memory's access is 20 times slower than the CPU. But CPU wants information only from the main memory, that is what is the von Neumann architecture says. However, so what we do, we cannot, now this is 20 to 50 times slower, technically slowing down the computer to a great extent. Right? You can build a very, very fast CPU, but no advantage. Why? Because it's very, very slow. Okay, so cache memory is a small fast memory between CPU and main memory, having access time closer to access time of CPU registers. So we bring in a fast memory, okay, in between the two. So why not just cache static RAM as main memory? Well, this would be very fast, but it will be very costly, as we had already stated this particular point. Okay, so fine, we can have a cache memory, but will it work? That's the question. So why does the cache increase speed? Well, the prime reason for that is locality of reference, and if you go to internet, they will talk about spatial locality and right, but and temporal, spatial and temporal locality, but let's understand the basic concept. So during program execution, what happens? Memory references by the processor for instruction and data tend to cluster. Program move from one locality to another. So what happens? For example, you are dealing with arrays. Aren't you going through the arrays repeatedly? Okay, so there is a cluster, okay, where you are working. You are dealing with some subroutines. You are clustering your basic execution in a particular area, right? So technically speaking, your main memory may be very, very big, but then multiple programs, these days multiple programs are going on, right? And you will be confined to very small area in the main memory which actually is being utilized. However, these localities, program move from one locality to another, right? So suppose you were working in, for example, in Word, then suppose you shift to Excel, then suddenly the locality changes. Even program changes their locality. They were working with one subroutine, now then they can subroutine or function, then they move to another function. So locality changes, right? So that way the locality is going to change. So this locality of reference you can experience in arrays, loops, etc. in your programs. Thus, large number of accesses to main memory are fulfilled. So what is going to happen? Now what we are going to do? We are going to catch the content which currently is required by the program, right? Which currently is required by the that is CPU for execution of the program into the cache memory. From the main memory we transfer it to the cache memory. Alright, and if we do that, so what is going to happen? The large number of accesses to main memory are then fulfilled by the cache because we have transferred it into the cache, thus reducing average access time. Not 100%, remember this, not 100% accesses can be from the cache memory. Many of them is going to be fulfilled by main memory, and that content will be brought to cache, and then only it will be supplied to the CPU. So that's how overall effectively we are going to enhance the overall speed of the access, in that sense reducing average access time. Okay, how does it operate? I think this will answer your query. CPU issues a request for content of memory location by specifying its address, and the addresses as we saw in the two chips which we discussed. It checks if requested data present in cache memory. If it is present in the cache memory, the data is returned from the cache. It is very, very fast. If it is not there, read the requested block from the main memory to cache and CPU. So we read it into cache and then it goes to the CPU and the processing then gets performed. Why we read it into the cache? Well, once again locality is the answer, because the data which has been referenced, or the program unit or some which has been referenced right now, there is a high probability that it may be referenced again. So that is why we try to put this particular information. So how to find which main memory address is in cache? Now this is a big question. Okay, so what we are doing, technically look into this particular domain. We have our programs and data into the main memory. That is essential. Alright. From main memory, we take some content into the cache. Now, which of this content is in cache? How do we know that? So, then we need tags. Okay. So, cache include tags to identify which block of main memory is in the given cache. Now, cache is organized into lines, or we can call it slots also. So, let us call it cache line. Okay. So, a particular cache line is just like a memory unit, right? That is the RAM cell, not cell, but particular 8-bit word or something, RAM word. Okay. So, that is how we are trying to understand that. Okay. So, let us try to see them with the help of few examples. First example, before we go to example, let us see this. So, cache size. Now, how the cache size will be looking like, okay. Cache memory are expensive, so kept smaller. Statistical suggest that even small caches enhances the processor performance. This is what we have been trying to say. This particular thing is defined over here. It is called the hit ratio. Okay, a typical cache size. Now, this is important. Suppose main memory is 8 GB. Okay, L1 cache can be 1 MB, L2 cache is around 8 MB, L3 cache is around 32 MB. So these are the three. L1 and L2 caches these days are built into the processors. Now processors have ultra large scale integration. So few caches have been built into it, and L3 are normally onboard cache. Your onboard cache is your motherboard, etc., which is your of your computer. So that is onboard cache. And main memory is also an onboard memory, so that is main memory stays over there, RAM chips are there, the SIMs or DIMMs, etc., which you use. So this RAM is going to be around 8 GB or so. Then the block size. Now this is very, very important. Now the block size is the unit of data it can be few memory words exchanged between cache and the main memory. So this is what we are going to say. RAM has one unit only, right? So one word of RAM, second word, third word, and so on and so forth, right? And that words are converted into block. It can be few words, memory words. So it can be 2 memory word or whatever, right? So this is how the block is identified in context of RAM, in context of cache only, right? Otherwise, main memory is just addresses, okay? So I'll try to explain this with the help of an example. So just hold on to this particular concept for a moment, okay? Then increase in block size increases the hit ratio. So if we have bigger block size, in general, it should increase the hit ratio, because suppose you are dealing with array, then the next value and the next value, so they will be transferred together. Okay, so the block size, the bigger is the block size, the hit ratio are increased, but too big a block ratio, the chances once again become smaller as we make the block size too big. That is also not a good thing, because once again the chances, I mean, there is a peak all the time, and this is the designers to decide what should be the normal block size. We'll take a very simple block size so that you can understand the importance of the block size, right? Okay. Then there is something called mapping. So the 3 terms which we have used, once again let us revise these 3 terms which we want to remember. First is that cache has tags, right? So main memory, there will be a word of main memory, right? So main memory is organized as a number of words. Then the next thing is, in the cache we have tags, and then each line, instead of word in cache we have a line. Each line will have a tag which will determine which memory words are there in the cache line. Okay, so that is how we have to identify. The next thing, next sentence you are going to remember is that block size, right? So this is basically how many words, memory words are there in a cache line. Okay, so that are exchanged in between cache and main memory is basically they will be transferred to one particular cache line. Okay, so the block size. So these are the few things. Now the next thing which you need to remember is the mapping. So mapping of main memory to cache. Where can CPU find a block of main memory in cache? So this is a big question. Alright, and there are schemes for it. And the 3 basic schemes are called direct mapping, associative mapping, and set associative mapping. All 3 have been discussed in your block, and let's discuss them with the help of few examples, not one. So the first example, okay. Now please note very this thing, though they are looks to be same block, but then cache is of very smaller size, right? So 2 to the power 9. Now first of all, 6 bits, there is a tag, there is an index. Now what is this? Technically this is a main memory address. It is of 15 bits. So main memory address is of 15 bits, and what we have shown here is octal address. Why we have shown octal address? Because it suddenly reduces the number of, like otherwise we would have represented 15 binary digits here. Now 3 binary digits are equal to 1 octal digit, right? So the number of digits we are showing are only 5 now. Right? Since it was 15, that's why we are using octal. If had been a multiple of 4, then we could have used hexadecimal also. So just for the sake of convenience, we are representing them with the help of octal. So this is my main memory. What are the addresses of, what is the length of address? 50 bits, which is equivalent to each octal bit, each octal digit is 3. That's 3 binary digits. So 3 5s are 15 digits equivalent, right? 6 bits, the tag has been shown as separately 00 followed by this particular. Now remember this particular thing here, the size of a word of RAM is same as size of cache, right? So this is 1:1 in this particular case. So 1 word of RAM equals to 1 line of cache, That means the block size of this particular RAM is 1. Okay, block size for this particular RAM as well as cache is 1 only. Okay, one word. Okay, not more than that. And 15 bits addresses means 2 to the power 15 is the size of this particular memory, and these are those addresses. What is going to be the smallest? All zeros. What is going to be the largest? All ones. So that is what is represented as 7 is 111, right? So this is what is octal. So this is all ones. Okay, so this is how the addresses will be looking like. Look into the octal addresses over here. The size of RAM, this is cache. Size of cache is 12 bits is the width and 2 to the power 9, right? So the overall, what is the octal address for one line of this particular cache? The 0001 and up to 50, that is 2 to the power 9. So 111, 111, 111. So this is 777 is the final address of this particular cache memory. Now, which of these RAM location, right? This tag field is going to determine which of these location are stored into this particular cache memory. How? This how is still not answered. So let's look into a simpler example now. Alright? And this example where our memory size is 256 bytes. So we have reduced, right? So memory size is 256 bytes. Byte addressable memory, that means one word of memory happens to be 1 byte. Alright? Okay. Then 256 words is equals to 2 to the power 8. Right? So this is what is, so our address is, main memory address is 8-bit long. So this is what will be 8-bit long. And then cache is of 32 bytes. The size of the cache is once again given in bytes, but one cache line is of 2 bytes. So this is what is slightly different now. So what we were saying here, the block size. What is the block size of cache? 2 bytes. So what we have done, we have created this particular word. This is memory. So this is my main memory. Alright. Let's look into these addresses. Byte 0, byte 1. Just to distinguish, this is word. So this is word 0, word 1, word 2, word 3, word 4, like that. But how the addresses has been done? They have been converted into block addresses. So this is my first block. Why? Because block size is 2. So main memory has first block, equivalent block of the cache. So this is what my first block. However, they are all distinctly addressed. So what is going to be the address of first byte, which is word of the memory? 0000000, 7 zeros, which is the block number. And the last bit is, for this particular byte is 0. For this byte is going to be 1. For here, what is going to be? 000001. This is going to be 0. This is going to be 1. So 0 and then this is 1. So address of this is 0000001. So this actually is location 4. Right? So location, sorry, 1, 2, 3, 4, like that. Okay? So this is how my main memory has been converted for the sake of demonstration in terms of cache. Otherwise, each location is independent. Alright? And they have been converted into blocks. So this is block 1 consisting of 2 bytes. Alright? And the first byte will be having address. The block address is 7 zeros. And the word address is 7 zeros followed by 0 for this word. And 7 zeros followed by 1 for this particular byte. So that is how my addresses are going to be in the main memory. It is same as the normal memory, just the blocks has been defined in this particular case. What about the cache? So this is the cache. So there is a tag in the cache. Alright. So there is a tag here in the cache. There is a line number in the cache. Alright. So what is the size of the cache? 2 bytes. 2 bytes means if I divide it by 32 by 2, right? So 1 line. So this is 1 line. Although I have still stated as word, but actually this represents 1 line, right? Just to equate it as word. Okay, so this is 1 line of cache and this line number is 4 zeros. This is the second line, okay, which represents byte 0 and byte 1. Why? 2 bytes are there, right? So this is how equivalent values has been shown. All right. So what is the length of this particular line address? 32 divided by 2 happens to be 16. So there are 16 lines of 2 bytes each. So these are 16 lines. You can say 0, all zeros till all 1. So 0 to 15. So we have the 16 line and there is a tag associated. So this is how the main memory we have converted into in terms of blocks, right? In the previous case we didn't have, the block size was 1 only, but here block size is 2. So 2 bytes are shown, two bytes, right? So word is a byte. So this is what you see, one particular block here, okay? So byte 0, byte 1, like that. So this is the cache line, byte 0 and byte 1 will appear in this particular case. Logical structure is not going to change. This is just for demonstration. Okay. Okay. So memory block size, you can see it is 2 bytes. All right. And that is what is shown in this particular slide. Okay. Now this is the direct mapping. All right. Each block of main memory can be placed only in one cache line. Now that is very, very important here. So this is how many bits? 8 bits. All right. So these 3, 1/4, then 3 and the word 0 or 1. So this is a typical memory address. All right. And this memory address refers to memory location. This 3 ones, 1 and these 4 over here. And this is 0. So we are referring to byte 0. You can see by color. Okay, so byte 0. So this is the address, that is all ones, that is if you compare it, it is 254. So this 254, this basically will be represented as last there will be a 0 here. So this will be equal to 254. And this last address is going to be actually 255. So this is size of main memory address happens to be 8 bits. All right, these 7 bits and 8 bit to determine which one of the two. Okay, so this is how most significant 7 bits specify memory block. These 7 bits are specifying the memory block as are the case over here, and these two are and the least significant 1 bit I identify unique word, that is byte in the memory location of 2 words. So which word we are referring to? Just I explained with the help of example. Now let's look into the direct mapping address structure. So in direct mapping, cache address is of cache size 32 bits, the same thing which we have used. Now memory block address. So this is what my memory address is. 111, 111, all ones and 0. So this is this particular byte we were referring to in the main memory. All right. Now where exactly in the direct mapping, how will I find? So what mapping scheme I am using? It's called direct mapping. I have not explained this direct mapping, but I'll be explaining it a little bit later. Okay, so this direct mapping, what you find that block address all ones, yeah, you can see by color, is mapped over here. All right, the all ones, that means 0001 will be mapped here. 000 will be mapped here, all these 4 bytes. Basically, how the memory address has been converted. This is to recognize the byte. Which byte? Byte 0 or byte 1? This is to recognize the block number of the, right? That is the line number of the cache. Okay. Now this is the memory block address. That has been divided into 2 parts, the tag and the line number. So the line number of this is always going to be this. Okay. What happens when these 4 bits are there? This tag number determines which of these addresses is available in this particular line of cache. Let's look into the example further. Suppose the memory block address, so this is memory block address and word. Which is this address? 001, I have shown it over here, 001, 000, and this is byte 1 we are referring to. So immediately we are referring to byte 1, that is what is represented here. 001, 0000, right? So what is the block address, the line number for this particular memory address? It's determined by these 4 bits. That is how the cache is going to be. So these 4 bits. And what is the tag number for this? 001. So this memory location is mapped here. In this memory location, this can also be mapped. 000 can also be mapped. Now this is the example of what we say direct, right? This is the what we have direct mapping scheme. In direct mapping scheme, the cache line will contain the 4 zeros, these 4 zeros. If these 4 zeros determines, if it is 4 zeros, this cache line. If it is 001, next cache line. If these 4 bits are 111, this particular cache line. So that is how we determine. So if I go simply, the memory address 0 will be coming to this particular address, 1 will be coming to this address, 15 will be coming to this, and the 16. Now this is 16 actually. So this will once again go to cache line 0, right? So how we will determine which is there? The tag number. If it is 0, then it is 0. If it is 1, it is 16th. If it is 010, it is 32nd location of the memory. If it is 011, it is 48th location. And 111 it is, then it is 112th. Alright? So 112th memory location actually is going to be stored in this particular location. That we are referring to block numbers only. Right? So this is 127th block. Remember this. Okay? So this is how. So this 127th block, right, is into 111. So this is 127th block is going to be stored here. Now this is something which is not easy, but you can understand this. Okay? But why do we need direct mapping? We need direct mapping. It is very simple. It is very inexpensive. And one major problem, if a program accesses 2 blocks that map to the same line repeatedly, then every access result in cache miss. So this is one of the problem of the direct mapping scheme. So therefore, the associative mapping scheme was designed. A main memory block can load into any line of the cache. Tag uniquely identify block of the memory. Cache needs to be examined simultaneously. Therefore, cache searching gets expensive on hardware. So this is what we say, that all these lines need to be, all these tags need to be organized. Now what I am talking about? Well, look into this particular mapping. The mapping problem here is very, very simple. How do we know? Suppose I am referring to a location, I want to refer to, I want to access memory location 16. Okay, so the memory location 16 is going to be this block followed by byte 1. Okay, followed by byte 0. All right. So followed by byte. Suppose I want to refer to memory location that is this particular location. In that particular case, right? In that particular case, I'll be just matching. Where can it be? This is the tag number. This is the line number which determines which line it can be. So if I know which line it can be, I simply match the tag number of the cache. If tag number of the cache matches, it's perfectly all right. Okay. If the tag number does not match, then the memory is not located in that particular line. It has to be brought from the main memory into that particular line, and accordingly this tag needs to be set. Okay. So this, as in associative mapping, this whole thing, okay, this whole thing is done in a very simplistic manner. All right. In this particular thing, all the tags, all the memory address except the word address is the tag. So we compare all the tags together. And if we need to compare all the tags together, obviously we will require a very strong circuitry, very expensive circuitry. That's why associated mapping schemes are very, very expensive. And we don't go for it. Therefore, we go for two-way set associative mapping. Alright, where we have the set number instead of the block number, we have the set number. Okay. And in one set we have two-way, means in one set we will have one way and two way. So in any of these locations, the memory can be, this memory location can be mapped. For example, you can see this, the tag number, when the set number is 111, this location is mapped, this is mapped into this byte, as well as over here this particular byte is 0011 has been mapped. So two memory location, 2 bytes can be mapped. In fact, these are the words. So 2 words have been mapped over here. 2 blocks have been mapped into this single cache set, right? So this is something which is not easy, but you have to refer to this, and I show a final example of this. This final example is, suppose now this is the main memory size is, let's say, 32 blocks, cache size is 8 blocks. Then in the fully associative memory, okay, the one which we showed, anywhere suppose I am looking for, now these are the block numbers, so block numbers have been merged into one, now there are no separate bytes, alright. So we have the 31s, okay, so we are just referring to blocks directly, so this will explain the blocks stuff. So you refer to 0 to 31 here, right? So because main memory size is 32 blocks, so we have 0 block, we have 31st block. Now let's try to see where the block number 28 can be. If the mapping is set associative, it can be any of the cache line, alright, any of the cache line can be there, it can be there. So we have to test every of these lines to find whether this main memory location is available in the cache or not. If it is direct mapping, then 28, and how many locations in total? 8, right? So 28 divided by, that is mod 8. So 28 mod 8 happens to be 4, right? So that is the 4th location where this particular can be found. So by using mod function, simply I can determine the direct mapping. Remember the table which I showed, 0, 1, 2, that is a mod operator, alright. And in set associative mapping, it can be in any of these 2 locations, okay. Why? Because 28, how many sets are there in total? There are only 4 sets, okay, set 0, set 1, set 2, set 3. So we divide 28 by 4, it has to be set 0, right. So modulo is 0. So it can be in any of these 2 locations, right. So this is the mapping scheme which you can follow in the main memory to cache memory. Now we don't have time for secondary storage organization, therefore I will be taking up this particular thing in the next session, because the next session on C programming is going to be very shortly after this particular session. So I will take another session talking about the secondary storage organization. But for the time being, let me try to wind up the information once again. What we are referring to, that whenever there is cache mapping scheme, what we really need to see, whether it is associative, whether it is direct, or whether it is two-way set associative. If it is direct, that is associative memory, then the location which we are referring to, that is the block we are referring to, can be anywhere. If we are referring to a particular block in direct mapping, what we will do, the number of lines which are there in cache, in this particular case, total 8 lines. So the address will be divided by 8. The remainder, what we will get, 4, that is the line direct mapping you will get. Otherwise, in two-way associative, once again divide by the set number and you will get it. Now, just to, before I wind up, I would like you to once again have a look at this after what we did the last diagram. This byte 0 and byte 1 are what? The location 000, 0000 followed by 0. This location is 000, 000 followed by 1. It is the byte 1. So let's look into once again this particular diagram so that I can make it clear to you. This is the cache lines, okay, and this is the locations which we are referring to. If I want to look into a memory address, 001, 00001, what is this equivalent to? This is a memory address which is technically the block number is the block number is 16. So this is what is the block number 16, and within that block word number we are looking to first byte. All right. So this block number first byte. So in the 16th that is block number, we are looking for word 1 and that's what you can see in this particular case. Okay. So this is the tag. All right. This is the tag. This is the block, that is the line number, and this is the word which you were looking at. This is the byte you are looking at. Now let's look into, we are looking for address 1. All right. So address 1, this that is 1 is going to be 0000001, and we are looking for byte 0. All right. So what you can see, this is my block number, this is my line number 0001, and this is my tag number. So tag number is appearing over here. All right. This particular case, let's look into once again. All right. This we have seen. Okay. So finally look into this. This is, we are looking to block number, the memory block number 127 and first byte of it. Okay. So memory address is going to be 1111111 followed by all 0. So that 0, actually we are referring to byte 0, and this 7 bits, this is these 4 bits, right? That is the line number is 1111 and block number is 111, right? So with this, I would like to end this particular session. Please go through this particular slideshow. Okay. Try to ascertain how the memory mapping is taking place, and if you still have queries, I think you will be having the queries. You must have queries because this concept requires some time to grapple with. Once you have the query, please do ask me we have created a group for MCS-12 on computer organization on Facebook. You can be member of it and ask queries on that particular group. Thank you for the time being. Bye for now. आज थोड़ा लंबा हो गया नहीं, वो कॉन्सेप्ट थोड़ा टफ था ना। हाँ